Hello everyone, I'm Daniele Sorini, a postdoc at Durham University in the UK, and I work at the interface of galaxy formation, large-scale structure, and cosmology. In particular, today I'd like to tell you about my recent work on the impact of baryons on the internal structure of dark matter halos. Indeed, I believe that this is a crucial question that we need to address if we want to achieve an accurate theory of galaxy formation in a cosmological context. And this is even more important in the view of the many surveys that are already bringing in, and others will bring in, a flood of accurate data which demands at least as accurate theoretical models if we want to avoid misinterpretation. And what I mean is that from a cosmological perspective, constraints on cosmological parameters can come from either early universe observations, such as the CMB, or late universe observations, such as the statistical properties of the distribution of matter, both dark and baryonic, which can be probed by some tracer, say galaxies. So clearly, understanding the impact of baryons on large-scale structure statistics is crucial if we want to get the cosmological parameters, such as the abundances of different components of the universe, right. But one might want to take this one step further and ask not only how much dark matter we've got, but also what type of dark matter is there. And in this respect, cosmological simulations have been really helpful in showing us that, for example, the number of substructures around halos is quite sensitive to the underlying dark matter model. For example, here on the left, you can see the projected dark matter density from a simulation in a cold dark matter scenario, and on the right, the exact same halo from a warm dark matter scenario. So in case of warm dark matter, the larger free streaming length of the warm dark matter particle can smooth out more effectively the density field around halos, hence producing fewer substructures. So clearly, dark matter matters also on smaller scales. So how can we probe that observationally? One example could be weak lensing, and the way it works is represented in this cartoon here. Suppose that you've got a bunch of galaxies in the background that are, say, randomly oriented. Now imagine that there is a large distribution of dark matter in the foreground, say around a cluster or something. Now, the light that is coming to us from the background galaxies can be bent by the distribution of dark matter in the foreground, and as a result we can see the images of these galaxies as slightly distorted. And so, for example, we could see that the orientation of such galaxies are no longer randomly oriented, but they follow some sort of coherent patterns. Now, my observer colleagues reassure me that you can use statistical tools to sort of undo the lensing effect from the image and at the same time reconstruct the distribution of dark matter in between. However, this is partially model dependent, and because the light is bent not only by dark matter, but by the entire matter distribution, dark matter and baryons, that's why we need to understand what baryons do to the distribution of matter also on smaller scales around halos. From a theoretical standpoint, this can be easily achieved with cosmological simulations. There are two main categories here. The dark matter only or n-body simulations, which, as the name suggests, contain only dark matter particles, so they are very cheap to run, but of course they lack all baryonic physics, and the hydrodynamical simulations, which include dark matter and baryons. So, for example, they contain resolution elements that represent the behavior of gas, stars, black holes. They can be very rich in physics. However, they can also be very expensive to run, which becomes an issue when you want to explore a wide parameter space of cosmological parameters, for instance. So, for this reason, it has become of great interest to consider some middle-of-the-road compromises where you run a few high-resolution hydrodynamical simulations to study accurately the impact of baryons on the distribution of dark matter on different scales, and then paint what you've learned on top of many dark matter only simulations which are used to probe a wide parameter space. Now, a useful metric that we can consider to assess the impact of baryons on the dark matter distribution on halo scales is the radial dark matter density profile. So basically, imagine to take a halo from the simulation, then you can draw concentric spheres around the center of this halo in an onion-like shape. And at that point, you can simply count how many dark matter particles you've got between two neighboring shells, and therefore you can easily get the mass density profile as a function of the radial distance from the center of the halo. Now, a key result from the late 90s is that the dark matter density profile of halos taken from a dark matter only simulation exhibits a nearly universal shape, which is accurately described by this formula here, known as Navarro-Franken-White, or simply NFW profile. As you can see, the NFW profile depends on only one free parameter called concentration, which occasionally is expressed in terms of its reciprocal, the length scale Rs, scale radius. Now, the physical meaning of the concentration parameter, as the name suggests, is that the higher the concentration, the more concentrated is the halo, meaning that more dark matter is in the center of the halo at the expense of the outskirts. Now, if we knew the dependence of the concentration on the mass of the halo and redshift, then we could plug this relationship into the NFW profile formula, and so for free obtain an analytical model for the dark matter density profile within halos without having to run a full n-body simulation. So that's why many authors became interested in this problem. And for example, here you can see a plot from the dark matter only version of the Eagle simulation, where every green point represents the concentration and mass of a halo drawn from the redshift 0 snapshot of that simulation. So you can see that there is quite a bit of a scatter, but then the authors organized the halos in halo mass bins, stack the density profiles, fit them with an NFW profile, and obtain the black points. Finally, they fit the black points with a power law and obtain the parameters that are reported here. So they repeated the exact same exercise for the full hydrodynamical version of the Eagle simulation. And here's what they found. Again, a power law, but this time with fit parameters that differ at a statistically significant level compared to what they found for the n-body variant of the simulation. So this means that if you want to represent the dark matter density profile of a halo of a certain mass and redshift with an NFW profile while accounting for the effect on dark matter introduced by the galaxy formation model embedded in the Eagle simulation, then you should use these parameters here at the bottom rather than the ones at the top. And this is also the context where my own work comes in. I wanted to extend the mass range considered, going from 10 to the 9 all the way to 10 to the 5.5 solar masses, so from dwarfs all the way to superclusters, and also the redshift range from 0 all the way up to 7, again motivated by the plethora of large-scale surveys which are becoming ever deeper and ever larger. So I've used the IllustrisTNG simulation, which comes with different box sizes and dark matter mass resolutions, and also the more recent MillenniumTNG simulation, which has essentially the same physics as IllustrisTNG, modulo some tweaks, but it has a much larger volume with 740 megaparsec per side, while retaining still a decent dark matter mass resolution. So, by combining all these simulations, I could leverage the larger boxes to probe with a higher statistics rarer and massive objects, and at the same time exploit the high resolution of the smaller boxes to study very well dwarf-size galaxies. And here is what I mean. In the upper panel, you can see the dark matter density projection around halos of different masses, from dwarfs on the left all the way to superclusters on the right, taken from the different simulations. And in the upper panel, you've got halos from the dark matter only variants of these simulations. Whereas the lower panels show you the exact same halos, but taken from the hydrodynamical simulations. And in fact, in the lower panels, you can see an overlay of the dark matter and gas density distribution. So to match the halos across the two simulations, I've exploited the unique IDs that are associated with the dark matter particles in each simulation. So basically, once taking a halo from a dark matter only simulation, I could ask myself, where do the same dark matter particles with those same particle IDs end up in the hydrodynamical simulations, and look for those exact halos. So this allows me to make an apples-to-apples comparison when it comes to analyzing the concentration-mass relationship in the two series of simulations, dark matter only and hydrodynamical ones. So in practice, after doing this matching, I could simply organize the halos in different halo mass bins and stack the density profiles and fit them with an NFW profile. And so I could easily obtain the concentration for the stack at a fixed halo mass and redshift. So let's have a look at the results for the concentration mass relationship at different redshifts in the n-body and hydrodynamical versions of the IllustrisTNG and MillenniumTNG simulations. At redshift 7, the concentration of halos in the dark matter only simulation is essentially constant, but that is not the case for the hydrodynamical simulations, where more massive halos are also more concentrated. Now, as we move towards lower redshift, 5 or 4, we can see that the concentration mass relationship in the dark matter only runs acquires a negative slope. Higher mass, lower concentration. But for the hydrodynamical simulations, we see a qualitatively opposite result. Higher mass, higher concentration. But that is not the case for all redshifts all the way down to redshift 0. In fact, at some point, we see that there is a break in the relationship for the hydrodynamical simulations. There is a mass scale of around 10 to the 11.5 solar masses, below which the concentration mass relationship is flattened. And above this threshold, instead, the results of the hydrodynamical simulation are actually not too different from the ones of the dark matter only simulation. So of course the question now is, why is that the case? And what does that mean for galaxy formation? Let's first consider a halo with a mass at or above the mass thresholds that we've just observed. Here we see the redshift evolution from 7 to 0 of the dark matter density profiles in the hydro and dark matter only runs, and also the gas and stellar density profiles taken from the hydrodynamical simulations only, of course. So at high redshift, the gas density profiles are steeper, hence there is a higher density in the core of the halo, which then increases the cooling rate and produces more stars. Now the higher concentration of baryons then drags dark matter further towards the core as well, thereby increasing the concentration. So this explains why at high redshift we see that in the hydrodynamical runs we've got a higher concentration compared to the dark matter only runs. Now, what happens at later times? Well, as time goes by, the abundance of dark matter increases due to accretion and mergers, etc. And accordingly, we see that the normalization of these dark matter density profiles increases. But for the gas and stellar density profiles, that is less so due to the action of feedback processes. Until a redshift 0, the baryonic mass fraction is lower, so the effect of baryons on the concentration becomes overall less important. In other words, the signal due to the baryons on the concentration mass relationship is diluted, and that explains why, at low redshift, above the mass threshold of 10 to the 11.5 solar masses, we see that the concentration mass relationship in the hydrodynamical runs is not too different from that in the dark matter only runs. On the other hand, in lower mass halos, the gravitational potential well is shallower in the first place, so fewer gas will collapse towards the halo center. And indeed, we can see that the gas density profiles here at high redshift have more of a core-like feature. So they will also produce fewer stars, and the overall lower baryonic mass fraction fails at further attracting dark matter towards the core of the halo, resulting in a lower concentration with respect to dark matter only case. And this explains why at high redshift we've got a lower concentration in the hydrodynamical runs with respect to the dark matter only run, and that is maintained all the way to down to redshift 0, where we see the flattening of the relationship. We tested different analytical fits to the simulation data, some from first principles models, for example the Ludlow et al. Model, but also from empirical models such as simply a broken power law. And we provide the fitting parameters for our best fit models, both for the dark matter only simulations and the hydrodynamical simulations. So in practice, you can simply take the fitting parameters that we provide in order to embed the concentration mass relationship as dictated by the physics ingrained in the IllustrisTNG and MillenniumTNG simulations within your favorite dark matter only simulation or semi-analytical model. To summarize then, I looked at the concentration mass relationship in the dark matter only and hydrodynamical variants of the IllustrisTNG and MillenniumTNG simulations, probing a very wide halo mass range from dwarfs all the way to superclusters and an ample redshift range from 0 all the way up to 7. I've discovered that at low redshift, the presence of baryons flattens the concentration mass relationship below a mass scale of around 10 to the 11.5 solar masses. In the paper, we provide the fitting parameters for our best fit models of the concentration mass relationship in all the runs considered, so that you can simply take those formulae and embed them in your favorite analytical, semi-analytical, or numerical models for the dark matter density profiles within halos. Thank you so much for your attention. Looking forward to discussing with you.